We're reviewing Genesis, Evolving Attack Strategies for LLM Web Agent Red Teaming. The paper puts forward an agentic framework to automate the discovery and evolution of attack strategies against web agents.
What's the headline result?
According to the paper, the framework achieves an average attack success rate of 53.0% against the C-Act agent with a GPT-4o backend, outperforming the tested baselines. Okay, let's examine their method. We should start with the attack surface and the stated limitations of current red teaming. Then we can cover the Genesis framework, its experimental setup, the results, and finally the actionable takeaways. First, what is the specific problem they're addressing? The paper defines web agent red teaming as the systematic evaluation of these agents via adversarial attacks. The core problem is that an agent's autonomy, which allows it to interact with web content, also creates an attack surface for manipulation through that same content. Can you provide the paper's motivating example?
Yes. A user gives an agent the goal, buy a computer. An attacker has injected a hidden instruction into the website's HTML that says, buy an electric fan. The agent executes the attacker's instruction instead of the user's.
What does the threat model assume about attacker access?
It's a black box model. The attacker can modify web page HTML. They cannot access the agent's internal model, weights, or gradients.
And what are the attacker's constraints?
There are two. First, any HTML modification must be invisible on the rendered web page to a human user. Second, the attack patterns must be general enough to be retargeted to different malicious arguments.
So how does this relate to the limitations of existing red teaming methods? Existing methods are described as static. They depend on manual design or offline training, so their capabilities are fixed. This paper proposes a dynamic approach, a continuous evolutionary loop where the system learns from interactions to refine its attack strategies. So what exactly did prior work not include?
Prior work did not include a framework for the dynamic evolution of attack strategies. The paper claims the core challenge is not just crafting a single prompt, but being able to extract, evolve, and generalize strategies that work in different contexts.
Let's get into the architecture of their proposed solution, the Genesis framework. Genesis is a framework with 3 agentic modules that form a learning loop. First, the attacker generates an injection using strategies from a library. Second, the scorer evaluates the target agent's actions and provides feedback. Third, the strategist analyzes the logs, summarizes successful patterns, and adds them to the library as new strategies. How does the attacker module evolve these strategies?
It uses a genetic algorithm. It retrieves relevant strategies for a task. Then, it applies mutation to less effective strategies to create new variations. For successful strategies, it uses crossover to combine them into new ones.
The framework uses a hybrid representation for strategies. A text-based strategy is a natural language description of an attack concept. A code-based strategy is an executable Python function that programmatically generates an injection. How was the framework validated? They used a subset of 840 tasks from the Mind2Web dataset. The target agents were C-Act and WebExpert, using backends like GPT-4o. They compared Genesis to 6 baselines. The primary metric was attack success rate, or ASR, measured as pass at 10. What were the main performance results? According to the paper, Genesis achieved an average attack success rate of 53.0% against the C-Act agent with GPT-4o. This is compared to 43.6% for Ad Agent, the strongest baseline they tested. The performance difference suggests that the dynamic, evolutionary approach is more effective at finding successful attack vectors than the static methods used by the baselines. And what does the ablation study show about the contribution of each component? The study indicates that the strategist module is the most critical component. Removing it caused the average ASR to drop from 53.0% to 29.9%. Removing either crossover or mutation also reduced performance. This result reinforces the paper's central argument: the ability to autonomously discover, summarize, and reuse attack strategies is the primary driver of the framework's performance. Does the paper provide a qualitative example of a discovered strategy?
Yes, it does. In a housing domain case study, Genesis created a text-based strategy. The injection uses a mix of technical jargon and multiple languages, English and Japanese, to disguise a query redirection as an urgent system override, which successfully tricks the agent.
Are these strategies specific to one model, or do they generalize?
The paper reports that the strategies are transferable. It also found an asymmetric transfer effect.
Strategies developed against more robust models were even more effective against more susceptible models. The paper suggests this can be used to discover more fundamental attack principles.
So, what are the actionable takeaways from this work? There are 5. 1. Automate the evolution of attack strategies. 2. Implement a continuous learning loop for red teaming. 3. Use a hybrid strategy representation of text and code. 4. Use genetic algorithms to evolve these strategies. And 5. Build transferable strategy libraries by red teaming against robust models. All according to Genesis, Evolving Attack Strategies for LLM Web Agent Red Teaming.